Hi everybody. So in this video we begin with Chapter 8, Complex Numbers. So let's begin with the learning objectives. By the end of this chapter you should be familiar with complex numbers in Cartesian form, z equals a plus bi, identifying real and imaginary parts, finding complex conjugates, and representing complex numbers in the complex plane. Representing numbers in polar modulus argument form, z equals r times cosine of theta plus I sine of theta is equal to r cis theta, and the Euler form, z equals r times Euler's number to the power of I times theta. Sums, products, and quotients of complex numbers in Cartesian, polar, or Euler forms in their geometric interpretation. Finding complex roots of quadratic equations with real coefficients, using de Moivre's theorem and its applications to powers and roots of complex numbers. So we begin with section 8.1, complex numbers. The development of complex numbers had its origin in the search for methods of solving polynomial equations. The quadratic formula had been used earlier than the 16th century to solve quadratic equations, in more primitive notations, of course. However, mathematicians stopped short of using it for cases where b squared minus 4ac was negative. In other words, they didn't know the solution to the square root of a negative number. The use of the formula in cases where b squared minus 4ac is negative depends on two principles, in addition to the other principles inherent in the set of real numbers, such as associativity and commutativity of multiplication. So the basic principles of complex numbers are: Rule 1, square root of negative 1 times the square root of negative 1 is equal to negative 1. And Rule 2, the square root of negative k is equal to the square root of k times the square root of negative 1 for any real number k greater than 0. So let's start with example 8.1, and it says work out square root of negative 36 times square root of negative 49. So notice that we can rewrite this as the square root of negative 1 times the square root of 36, and this times the square root of negative 1 times the square root of 49. Then we can rearrange it as the square root of negative 1 times the square root of negative 1 times the square root of 36 times the square root of 49. And then from here we're going to get negative 1, this is rule number 1, times square root of 36, which is 6, times square root of 49, which is 7, and we end up with minus 42. To deal with quadratic formula expressions that consist of combinations of real numbers and square roots of negative numbers, we can apply the rules of binomials to numbers of the form a plus b square root of negative 1, where a and b are real numbers. For example, to add 5 plus 7 times the square root of negative 1 to 2 minus 3 square root of negative 1, we combine like terms as we do with polynomials. So we end up with the expression 7 plus 4 times the square root of negative 1. Similarly, to multiply these numbers, we use the binomial multiplication procedures. So if we multiply 5 plus 7 times square root of negative 1 times 2 minus 3 times square root of negative 1, you can see that you'll end up with 31 minus square root of negative 1. Square roots of negative numbers were given the name imaginary numbers, and Euler introduced the symbol I for square root of negative 1. A pure imaginary number is a number in the form k times I, where k is a real number and I, the imaginary unit, is defined by I squared equals negative 1. So from now on, instead of using square root of negative 1, we are going to use the symbol I. So we continue with example 8.2, and they ask us to simplify a couple of expressions. So for a, we have the square root of negative 36 plus the square root of negative 49. Now, remember the principle, I squared is equal to negative 1. So we can rewrite this as square root of 36i squared plus the square root of 49i squared. And then from here, we're going to get 6i plus 7i, which gives us 13i. For B, we have the same example as 8.1. Square root of negative 36 times square root of negative 49. We can apply the same principle. So this would be square root of 36i squared times the square root of 49i squared. So notice that this is going to give us 6i times 7i, and this equals 42i squared, or negative 42, which is consistent with the previous answer. Gauss introduced the idea of complex numbers by giving them the following definition. A complex number is a number that can be written in the form a plus bi, where a and b are real numbers, and I squared equals negative 1. A is called the real part of the number, and b is the imaginary part. It is customary to denote complex numbers with the variable z. Z equals 5 plus 7i is a complex number with real part 5 and imaginary part 7. And z equals 2 minus 3i has 2 as real part and negative 3 as imaginary. Notation. It is usual to write REZ for the real part of z and IMZ for the imaginary part. So RE, 2 plus 3i is 2. And IM, 2 plus 3i equals 3. So we continue with example 8.3, and they want us to simplify a few expressions. So for A, it's going to be 4 minus 5i plus 7 plus 8i. So we treat this as a normal algebraic expression, and we add the real parts and the imaginary. So this would be 4 plus 7, which is 11, and minus 5 plus 8, which would be 3i. For B, we have 4 minus 5i minus 7 plus 8i. So here we do the same thing, except that now this negative sign over here is going to change the signs of the numbers within the parenthesis. So this is going to be minus 7, and this is going to be minus 8i. In other words, we're going to get 4 minus 7, which is minus 3, and then minus 5 minus 8, which is minus 13i. For C, we're going to multiply these numbers. So it's going to be 4 minus 5i times 7 plus 8i. And here we just apply the distributive property. So 4 times 7 is 28, plus 4 times 8 is 32i, minus 5i times 7 would be minus 35i, and then we would have minus 5i times 8i, and that's going to be minus 40i squared. So here notice that I squared is negative 1, so this is minus 40 times negative 1. In other words, this is plus 40. So we're going to end up with the complex number 68, and then 32i minus 35i would be minus 3i. So next we have division, and it says that multiplication can be used to perform division of complex numbers. And we go into example 8.4, and it says find the quotient of 2 plus 3i divided by 1 plus 2i. Now in the book, in this example, they solve it in a very complicated way using a system of equations. But it's a lot easier to use something called the conjugate. So if you have z is equal to 1 plus 2i, then the conjugate of z, which is symbolized with this asterisk, would be equal to 1 minus 2i. So basically the conjugate is simply the imaginary part with the opposite sign. Notice that we leave the real part the same. So 1 minus 2i. So what we do is that we multiply this expression by 1 minus 2i over 1 minus 2i. So notice that we simply do the distributive property for the top as we did in the previous example. And we're going to get 2 minus 4i plus 3i and then minus 6i squared. And this over, and this is the interesting part, notice that if we multiply these two expressions, the denominators, it's a difference of squares, right? So this is 1 minus 4i squared. Now it's important to remember that I squared is negative 1. I squared is negative 1. So that means that this is going to be plus 6, and this is going to be plus 4. So we're going to end up with 2 plus 6, which gives us 8, minus I over 1 plus 4, which is 5. But you never leave the complex numbers in this form. You want to separate the real part from the imaginary. So this is going to equal 8/5 minus 1/5 I. So let's talk a bit more about the conjugate. With every complex number, a plus bi, we associate another complex number, a minus bi, that is called its conjugate. The conjugate of number z is most often denoted with a bar over it, sometimes with an asterisk to the right of it, occasionally with an apostrophe, and even less often with the plain word conj, as you can see in these examples. In this book, we will use z asterisk for the conjugate. In your own work, you can use any notation you feel comfortable with. You just need to understand that IB questions use the conjugate notation z asterisk. The importance of the conjugate stems from the following property. If you have a plus bi times a minus bi, this is going to be a difference of squares. So it's going to equal a squared minus b squared times I squared, which ends up being a squared plus b squared, which is a non-negative real number. In other words, the product of a complex number and its conjugate is always a real number. So we continue with example 8.5, and it says, find the conjugate of z and verify that z times its conjugate is a real number. So for a, we have that z is equal to 2 plus 3i. Therefore, its conjugate is going to be 2 minus 3i. And then notice that z times its conjugate is going to be 2 plus 3i times 2 minus 3i. And we already know that this is equal to 4 plus 9, which is 13. And that is a real number, of course. For b, we have that z is equal to 5i. So its conjugate is going to be minus 5i. So z times its conjugate is going to be 5i times minus 5i, and this is going to be minus 25i squared, which equals 25. And then for c, we have that z is equal to 11. Now notice that this has no imaginary part, so its conjugate is going to be 11. Therefore, z times its conjugate is simply 11 times 11, which is 121. So we continue with example 8.6, and it says, find each quotient and write your answer in Cartesian form. So Cartesian form just means separating the real part from the imaginary, right? Okay, so for a, we have 4 minus 5i divided by 7 plus 8i. But we already know that all we have to do is multiply by the conjugate, which is 7, the conjugate of the denominator, which is 7 minus 8i, and then also on top, 7 minus 8i. So we have distributive property for the numerator, and here we're going to get 28 minus 32i minus 35i plus 40i squared. And in the bottom, we know that it's simply going to be 49 plus 64. And we also know that this is minus 40. So we end up with minus 12 minus 67i over 113. And we separate the real and imaginary parts, and we end up with minus 12 over 113 minus 67 over 113i. Now for b, the same thing again, right? So 4 minus 5i over 8i multiplied by the conjugate of the denominator. So minus 8i over minus 8i. And here we're going to get minus 32i. And this is minus 40. And this over, notice that it's going to be negative 64i squared, which is just 64. So rearrange this, and we get minus 40 over 64 minus 32 over 64i, and this can be simplified into minus 5 over 8 minus 1/2 I. Now for C, we don't have to do anything, right? Because the denominator does not have any imaginary part. So we can just leave it as 4/7 minus 5/7 I. So let's continue with example 8.7, and they want us to solve a system of equations and express the answer in Cartesian form. So this is the system of equations, and obviously they want us to solve for the imaginary numbers z1 and z2. So there's a couple of things to notice here. First of all, this can be expressed as 3 times 1 minus I, which is the same thing we have here. And also, this is the conjugate of 1 minus I. Then, because we want to eliminate one of these variables in order to solve for the other one, notice that if I multiply this by 2 and this by 1 plus I, because on top, I'm going to get 2 times 1 plus I times z1 minus 2i z2 is equal to minus 6. And then for the bottom part, I'm going to get also 2 times 1 plus I times z1. And then here I have a conjugate. Notice that I have 1 minus I times 1 plus I. So that's just going to be 1 plus 1, which is 2. So 2 z2. And then over here, I'm going to get 3 times 2, so 6, right? Because remember that if I multiply this by this, it's going to be 2. So 3 times 2, which is 6. So now what I can do is subtract the bottom equation from the top one. So this is going to cancel out, and I'm going to get minus 2i minus 2 times z2 is equal to minus 12. So that means that z2 is equal to minus 12 divided by minus 2 minus 2i. And then we can do this separately, right? Multiplying by the conjugate again, and we're going to get 3 minus 3i. So that's going to be z2. So now we can substitute for z2 in the first equation, and notice that we're going to get that z1 is equal to minus 3 plus I times 3 minus 3i, and this over 1 plus I. And from this in the end, we're going to get 3/2 plus 3/2 I. So this would be the solution to the system of equations. So in the next slide, you're going to find properties of conjugates, and you can check these out on your own together with their proofs. And then next, you're going to look at something that says conjugate zeros of polynomials. And basically, it's this rule. If C is a root of a polynomial with real coefficients, then its conjugate is also a root. And then here you have the proof, which you can check out on your own. So now let's take a look at example 8.8. And it says 1 plus 2i is a zero of the polynomial p of x equals x cubed minus 5x squared plus 11x minus 15. Find all other zeros. So this is to the power of 3. That means that it's going to have 3 zeros. And we already know what the other zero is because it has to be the conjugate of this. So if this is 1 0, the other 0 is 1 minus 2i. And let's suppose the third 0 is just c. So notice that if we have a polynomial, like p of x is equal to x cubed minus 5x squared plus 11x minus 15, this can also be written as the multiplication of x minus its zeros. So notice how we could write it as x minus 1 plus 2i times x minus 1 minus 2i, and this times x minus c. So we can rewrite this as, notice here, we can rewrite this as x minus 1 minus 2i times x minus 1 plus 2i, and this times x minus c. But notice that these two numbers are the conjugates of each other. So we could write this as x minus 1 squared plus 4, and this times x minus c. And then if we expand this to the left, we're going to get x squared minus 2x plus 1 plus 4, so plus 5, times x minus c. And then after this, if we apply the distributive property between those two expressions, notice that we're going to get x cubed minus cx squared minus 2x squared plus 2cx plus 5x minus 5c. And then if we group similar terms, we end up with x cubed minus c plus 2 x squared plus 2c plus 5x minus 5c. And then now we can compare the original polynomial with this to solve for c. So notice that here for x squared, we have minus 5. So that means that c plus 2 has to equal 5. And then notice that for here, 2c plus 5 should equal 11. So 2c plus 5 should equal 11. And finally, minus 5 times c, minus 5 times c should equal negative 15. So notice that for all these three equations, we have the same solution. C is equal to 3. Therefore, we found all the zeros for the polynomial.